So you see, this is slow cooling, right? We are just doing the same thing. Slow cooling means equilibrium cooling. Equilibrium cooling. So we are just explaining the same thing to you. So there is no major issue that when we cool it, then initially one of the metals will start to solidify. Further cooling, the other metal will start to solidify, and there will be this structure of alpha and beta and so forth, right? If we cool fast, then some cores, right, will be formed, cored structure will be there. So now what you uh, like very much, I have written self-study there, but I will still go through it because initially when I was planning, I thought you can do it, but I will go through it quickly with you. The question is that you have a lead tin alloy system. So the lead tin phase diagram will be there, and they say make phase analysis. Make phase analysis. Make phase analysis means do all the four parts. All the four parts. At any given temperature and so on, what are the phases, what are the compositions of the phases, using lever rule, what are the mass fractions of the phases, and what is the diagram in which you can show the structure. So whenever they say make phase analysis, then they want all the things. So now at the eutectic composition 61.9%, just below 183 Celsius, that is one question. Then take a 40% tin alloy at 230 Celsius, then right, and so on. So those question points we have marked here already. They are actually the same ones as we did for you earlier, right? So that is why I said it is a self-study, because we have already done it. First question was eutectic composition. So 61.9% and just below 183. So you are coming from here, just below 183. What will we have? We will have only solid phase alpha plus beta. All of it will be eutectic alpha and beta, and this will be the diagram. This will be the diagram, right? Um, about the lever rule, I will tell you later. And if we take the second and third and the fourth parts of the question, 48% tin at point A, at point B, point C, point D, and so on, what will happen? So that is what the diagrams we have already discussed, but the lever rule and so on we can show you. So you see, if for example we are here, if we are here, what is your first answer? There are, right, so we are saying this given temperature, it was 230 or something, at we are at point C, the original was 40%. Your first answer is there are two phases, solid alpha and liquid. For second answer, you draw a tie line here, right? You draw a tie line here, see where it cuts the liquid, find the composition. Where it cuts the solid, find the composition. So second answer would be, what is the composition of the solid phase? What is the composition of the liquid phase? Note down those values. And for the third part, you draw the same tie line is your lever rule. Here is the weight percent solid, here is the weight percent liquid, and here is the original composition 40. So now what is the mass fraction of the liquid? This value minus this value upon the total. What is the mass fraction of solid? Opposite side, this value minus this value upon the total, right? So that is what they are doing there. So just go through these, right, at 61.9%. Now this is important. You see, just below 183 Celsius. So go back to the diagram. I can't go back here, but go back to the diagram. Just below 183 Celsius, make a tie line. Just below, not right, just below. Just below means assume that it is the tie line. So tie line, it is the tie line at the eutectic temperature 183. You will see that it goes there and cuts alpha at 19.2%, and it goes there and cuts the other one beta at 97.5. So right, so alpha point is 19.2%, beta point is 97.5%, and then you can write whatever you have, right? If you want to find alpha, you go to the other side, you say 97.5 minus the original 61.9. upon the total, right? You see, your tie line at the temperature of 183 Celsius cuts alpha at 19.2, cuts beta at 1997.5. So these are the values. When you find the weight fraction or mass fraction of alpha, then you go to the other side, right? 97.5 minus original upon total 97.5 minus 19.2. When you want to go for weight percent beta, you go to the other side. So 61.9 minus 19.2 upon 97.5 minus 19.2. The others are simple. At 230 Celsius, find the values, write it, right? So that is why I wanted to show you again that when, forget about this one, we are talking going back to 61.9%, 61.9%. So they are saying just below it. So just below it is almost the same line. So it goes, cuts alpha at 19.2%. It is given. It goes to the right, cuts beta at 97.5%. So when you say just below the eutectic point or at the eutectic temperature, beta is 97.5% tin and alpha is 19.2% tin. The other values you have already known, so you continue with it and you will find at point D, which is, now this point D is nice. When they say 183 plus delta T, delta means just above it. So you don't actually go above, you go to the same line. You go to the same line. You go to the 183 Celsius line, right? So therefore you will know that it cuts alpha at 19.2. Just above it is the same. When you say just below it, it is still the same line. So you cut at 19.2 and you cut at 97.5, right? But when you were here, it was liquid and alpha. When you are here, you are talking of alpha and beta. That is happening. But when you are at 183 or you are at 183 plus delta T just above it, or you are at 183 minus delta T just below it, you are still at roughly the same point. So you are not very different. So therefore, the readings that you cut, 19.2% alpha and 97.5% in beta, these values are still there and you calculate it. So I would really urge you that we have done many examples, but this last example, right, during the lectures we also explained it, but this example you have done with me. But then, as we always ask you, that write down the question, open the phase diagram as if you don't know where the lines are, and then start. If you have a hard printed copy of the lectures, then on the diagram, take a scale, take a sharp pencil, try to draw a vertical line at the given composition, try to draw a horizontal line at the given temperature, and then start the work, right? If you have to draw a tie line, then see where the liquid is being cut, draw a vertical line there with your sharp pencil and scale ruler. Where the tie line cuts the solid, there you draw a vertical line. So please practice it, right? Do the same example 1 time, 2 times, and you will be pretty good, right? With this, we have come to the end of the chapter. So very quickly, I will summarize it for you. The chapter is called phase diagrams. So we explained what is a phase diagram for you. We explained phase diagram initially for pure materials like water, and the phases are solid, liquid, gas, and you know them as ice, water, and steam. Another pure material, we took the most famous metal, iron, but its phase diagram was a little different because we have 3 solid phases of iron, alpha, gamma, and delta, right? BCC, FCC, and again BCC. Then we told you that if we now have a mixture of more than one material like water and sugar, then how do we treat the phase diagram? So we come into solubility limit, how much sugar at any given temperature can be dissolved in water and so forth. Then we gave you an example, I don't remember, of copper nickel, just as an example, that the 2 materials are both metals. So you completely melt them mix them so that they become a mixture or a solution, and then solidify them. Then you will call it a solid solution. After this initial background, right, and then we told you about, sorry, initial background still continues in cooling curves, that you see how do things cool. So for any metal, it is at very high temperature completely liquid. You drop the temperature until it starts to become solid. If it is a pure metal, because of latent heat of fusion, the temperature will remain constant until the whole metal has solidified. Once the whole liquid has changed into solid, the temperature will again start to drop. If it is a material like iron, which has many solid phases, then you have complete liquid. At some temperature, it starts to become delta solid, right? Once it has become that, after more dropping of temperature, it starts to become gamma solid. Then if you drop the temperature further, it starts to become alpha solid, right? So this was cooling curve. Then we started with actual phase diagrams of alloys, and I don't remember, maybe it was a copper nickel system, and so on, right? So we said that we will start with a binary isomorphous alloy system. Binary means that there are two metals for which we are doing the phase diagram. In a phase diagram, the vertical axis will always be temperature, the horizontal axis will always be composition in weight percent of the material or mass percent of the material. And we then saw that there is a liquidus line and there is a solidus line. And you already know the questions and so forth. So there is a tie line to find things. Then we did examples and so on. We did an example on silver palladium also and so forth. And we talked of equilibrium cooling. We talked of non-equilibrium cooling and core structure. We talked of using cooling curves of pure metals and of different compositions to make the whole phase diagram and so forth. This ended the binary isomorphous alloy system. Then today we started the eutectic, binary eutectic. It is still binary, so there are two materials, for example, lead and tin. But there is one special point. Normally, there are two solids, alpha and beta, so it is non-isomorphous. But on one side, when you start to cool, the liquid becomes alpha plus liquid, and then it becomes alpha plus beta. On the other right hand side of the diagram, the liquid, when you cool it, becomes beta and liquid, and then it becomes alpha plus beta. But there is one point which is the eutectic point, where the liquid suddenly becomes alpha plus beta, two solids. That is called the eutectic reaction. We did examples, lots of examples at the eutectic composition of 61.9%, at a given composition of 48% tin, and so on. And hopefully you will do all the examples that we have done during the lectures again and again, so that you become very good at it, but without looking at the solution, right? So this is it, and we have completed chapter 8. Next chapter is chapter 9, which is sort of a continuation of this. So next time when we see you, we will inshallah start chapter 9, and hopefully I will upload that chapter to your Moodle, and this lecture also I will upload as a Moodle to you, and also we will send you some emails, so please keep on looking for your emails. Thanks a lot. Ma'as salama.